Hello, you are watching the 25th part of a sequence of videos about parametric curves. It's part 4 of a sub-series about modeling the trajectory of a ball, whether it's thrown or shot out of a cannon. In general, you call such a thing a projectile. We've been emphasizing some key facts from calculus, though if you don't know calculus, I think you can still get things out of this because I emphasize physical geometric meanings of things. And in this video, we're going to focus mostly on the fact that the distance traveled can be found via something called integration of the speed function. In the first 20 or so videos, I focused on motion along a straight line both at constant speed and at non-constant speed. And what I did was that I drew in some right triangles and used the Pythagorean Theorem, really the distance formula, to find what I call dist of t. That's the distance traveled function. It tells you how far you've traveled from time 0 to time t. And then what I said was that you could use a calculus operation called differentiation, which calculates something called the derivative of the distance traveled function, denoted dist prime of t instead of dist of t. And I said that that gave you the speed function, speed of t, which gives the instantaneous speed at any moment in time. Geometrically, the speed function, dist speed of t, gives you the slope of the distance traveled function at that moment in time t, more technically the slope of its tangent line. If you're in a car traveling, the speed of t at any moment in time t is what your speedometer says at that moment of time. Let's go down to the example we've been doing recently, which is modeling the trajectory of a ball as it's shot out of a cannon, say. We are using some physical principles to derive some parametric equations. Actually, I didn't do the derivation, I just made these equations up, but these are physically realistic. This 4.9, for example, comes up from some physics principles. And we, down here, made some plots on Mathematica showing the motion of the ball. Here we go. In the upper left corner, we've got the ball moving. You see two black arrows, though it's hard to see the tips of the arrows. The position vector is pointing from the origin to the ball as it moves, and its velocity vector starts at the location of the ball and points along the direction of motion, tangent to the direction of motion. Its length is equal to the speed. The speed function is down here in the lower right. It's the length of that velocity vector. It starts out around 36 and goes down to a low of 30 when the ball is at its peak. This graph up here in the upper right is the graph of the y-coordinate of the ball as a function of time. Notice the scales on these two axes are different. And this one is the graph of the x-coordinate as a function of time. Look at it sideways. Alright, so we want to now emphasize how to calculate the distance function. Once again, back with straight line motion, the order that we did things in was that we calculated the distance function first by using the distance formula, and then we used the derivative to calculate the speed function. Here I said the velocity vector is the derivative of the position vector and that the speed was the norm of the velocity vector, its length, which can be calculated on Mathematica like this. I got rid of the absolute value function in there because I'm squaring. This is the simplest form of the speed function that we can use here. What do we do now, though? We want to use that to find the distance traveled function. Here is the idea in symbols and in principle. I said that the distance traveled, the area under the speed graph, okay, this is another point of emphasis that I make. The area under the speed graph from 0 to t gives you the distance traveled from time 0 to time t, in fact the value of dist of t. And I said you can use something called an integral symbol in Mathematica, and by hand for that matter, that represents that area. The starting value of time is 0, the ending value of time is t, and the function we're finding the area under is the speed function, speed of t. Now it's kind of bad notation here to use the same letter for this function argument that I use in this upper limit of integration. It's kind of bad notation. Some people do it anyway, but it's sloppy. It's better to use something else. I'll use a Greek letter, tau, which is the Greek version of t, for this function here, this integrand it's called, the function you are integrating. You have to put a d tau here as well to emphasize that the variable for this function is this letter tau. Again, This quantity for any value of t is going to give you the area under the graph of the speed function from 0 to t, and the claim is that that is the same as the distance traveled at time t, meaning the distance traveled from time 0 to time t. However, in Mathematica, I'll just go ahead and show this to you. If I enter this and then try to go down here and plot the distance traveled function along with the speed, it does have some trouble. It doesn't quite work. It might even abort the calculation, so to speak. Let's make the distance traveled thick blue. I think this may not work. Let's see what happens here. I'm going to run it. It's calculating a lot. It's running. And it's either going to, yeah, it was aborted. Okay, it was either going to run really slowly or be aborted. It was doing so many calculations with a complicated function to integrate that it was having trouble. So there's two ways around this. One way always works. Here's the way that always works. Use a command in Mathematica called nintegrate, which does something called numerical integration. Don't worry about what that means. It's just another way to calculate the area under the graph of the speed function here. I'll put the speed function in here. Once again, use the letter tau instead of t. Tau is going to go start at 0 and go up to t. Tau does represent time. T is a fixed time, tau is a variable time. Let's see if I enter that if the code runs faster. And it runs at all. It looks like it's going to run. Yes, and it is running faster. And yes, I do get a blue graph. Looks like a straight line. It's actually not a straight line. I do see it goes up higher. That's because the distance traveled is going to be over 120. I better change the scale here. Let's go up to, say, 150 instead of 50. See what happens. There we go. You can see the entire blue graph. It looks straight, but looks are deceiving. It's actually not straight. Remember that the red graph, the speed function, gives you the slope of the blue graph. Since the red graph is not constant, it goes down to 2 and then goes back up. That means the slope of the blue graph can't be constant. It's got to be higher here than it is in here. This is the low slope here, and then the slope has to be higher here again. So that's a bit deceiving. You got to be careful in thinking that's a straight line. It's not a straight line. It is close. It certainly looks like a straight line, but it's not. So once again, I've just emphasized that the value of the red graph, the speed function, gives you the slope of the blue graph. What about the area under the red graph giving you the value of the blue graph? Remember, we can shade in some areas here by adding some options. And in fact, I think I'm going to need to separate this with a show if this is going to work. Let's see, I'm just going to graph the speed function first of all. Show combines graphics. So first I'm going to graph the speed function within the show, but I'm also going to graph the distance traveled function here. I'm going to put another plotting command. Copy and paste this. Put it after the comma, change the word speed to dist, change red to blue. And I would like to shade area under just the red graph. That's why I did all this. And filling arrow axis should do what I want. We're shading the area under the red graph. The claim again is that the area under the red graph over any time interval gives you the value of the blue graph. Does that seem reasonable here? We'll end this video by thinking about if it seems reasonable. We'll go out to time 4. What's the area of this shaded region? It's a little smaller than a rectangle that would have a base of 4 and a height of about 30, what was it, 36 or something? 36 times 4 is 144. That would be the area of a rectangle whose top would go like this. This area is a little less than 144. In fact, it's the value of the blue graph, which is less than 144, maybe somewhere around 130 or so. Okay? So we are visually trying to confirm that. We'll get into more detail in the next video.